you want me to talk about what's going on there? I'm gonna do it anyway. But okay, so yeah, this paper I think is best described as the third in a series of papers. I'll talk about the first two first for context, and I'll talk about mine. So paper one is this paper by Power et al. At OpenAI, where they introduce this phenomena of grokking. This phenomena where if you train small models on algorithmic tasks, they will initially memorize the training data, achieving very, very low training loss, and then appear to not do much for a while. They appear to just not do anything for a large number of training steps, and then later on, they will very quickly generalize. And this is pretty weird. In the original paper on grokking, they weren't able to understand what was going on here. And there's been many follow-up papers which have attempted to understand what's going on. I'll focus on two, this one and a prior work. The prior work of interest is by my co-author Neil Nanda. In that paper called Progress Measures for Grokking via Mechanistic Interpretability, what he does is he tries to understand how networks do a particular task, this modular addition task. And what he finds is pretty weird. Step one of how he attempts to understand grokking is he uses mechanistic interpretability. He tries to engage with the computation occurring in the model and understand what features the model is learning and what algorithms it's implementing by staring at the model weights. And how he does this is he takes this trained model and he stares at the activations of the weights very hard and is able to figure out what it's doing. And what it's doing is weird and involves Fourier transforms and trig identities. It's pretty cursed, but if you think about it for long enough, it makes sense, and it seems intuitive from the network's perspective. And by understanding the algorithm and the network implements, he's able to track the development of this algorithm over training and understand what's going on in this grokking plot. I won't explain what's going on there, but feel free to ask afterwards. Now, in our paper, what we ask is, how do networks do this more general task of group composition? The cyclic group, modular addition is just composition on the cyclic group. So you can very easily generalize the task to any group and conjecture that the network might implement this algorithm, which is a direct generalization of the algorithm Neil found that involves Fourier transforms, that involves some more abstract mathematical machinery called representation theory. So this is what we guess the network is doing. We train a network to perform composition on this group S5, this group of permutations of 5 elements. And we apply a similar approach. We apply mechanistic interpretability. We try and understand what algorithm the network implements, what features it's using. And we recover exactly the algorithm that we conjecture. We find that the network memorizes these representation matrices in its embedding layer, and then manipulates them to give you the right answer. And we have various evidence to suggest this is the case. Then we want to generalize. We want to ask a question about this universality hypothesis of mech-inter. We want to ask, do networks learn the same algorithm when trained on similar algorithms when trained on similar tasks, or not? Early work on mechanistic interpretability at OpenAI found that image models tended to learn similar features in early layer neurons. So if you apply feature visualization to early layer neurons of models of different architectures, you find similar looking things. You find these curve detector and high-low frequency detector neurons. Now, one worry is that this work is very cherry-picked. These neurons are very cherry-picked, and this is not representative of what is actually going on. In our work, we try and be a bit more precise. We try and systematically understand universality. So what we do is we train networks to perform group composition across many, many different groups. Here are all the groups we use. I would have liked to do more, but I ran out of time. And we find that in each case, the same algorithm is learned, which is fun. So this is evidence of weak universality, we say. After that, we zoom in a bit further. We ask, so there's some freedom in this algorithm about what your representation is, what your choice of row is. So we study which representations networks use, and generically find that networks trained on the same architecture, on the same data, so we train on the same group, on the same architecture, and all we do is we change a random initialization. We find if we do this, networks will stochastically choose different representations, different features. And this is somewhat surprising, given that some representations, some features, are definitely better than others. Some are simpler, some are more performant, etc. So I guess the takeaway from this is strong universality seems false. I suspected this was the case from the start, but it is good to have some evidence. And interpreting one network seems insufficient for understanding one behavior in general. Initially, what we did in this paper is we interpreted one network very thoroughly, and we only found 2 of the possible features. We only found 2 of the possible representations, when in fact, there were 6 possible features that the network could learn to solve this task. And only by studying many, many more networks will we be able to recover the rest of the features, the rest of the representations. Cool. Any questions?